Welcome back to Mechanical Engineering Made Simple. Today we are taking, well, a monumental leap. We're diving into a realm where history, myth, and some really cutting-edge RF engineering all collide.
That sounds exciting.
Yeah, we're doing a deep dive into the foundational ideals of Nikola Tesla for wireless power transmission. And maybe more importantly, how modern engineers are actually translating that, century-old vision into practical, scalable architectures.
Right.
We're even going to detail how you can build your own miniature tower at home and what kind of supplies you might look for.
Exactly. And for generations, this dream, this wireless power idea, it's been kind of trapped, hasn't it? Stuck in this, technological purgatory, somewhere between incredible genius on one side and, frankly, outright science fiction on the other, often overshadowed by that romanticized story of Wharncliffe.
Yeah, the big tower, the myth.
Right. So our mission today is really to pull this topic firmly back into the engineering lab. We're defining the scope by dissecting these concrete, testable architectures, what we're calling the Wharncliffe 2 prototypes. These adapt Tesla's core principles, but crucially, they adapt them to modern constraints. Physics, regulation, safety.
And most importantly,
The absolute imperative to move actual watts reliably from point A to point B. That's the bottom line.
gotcha. And we've got quite the archive guiding this deep dive, right? We're not just going off the legend.
No, definitely not. We have Tesla's foundational patent document specifically, US 645576. And alongside that, excerpts from his actual experimental logs, the Colorado Springs notes. Very revealing stuff.
Okay, so the original source material.
Yes. And we're contrasting this historical thunderstick, as you called it, with modern, pretty comprehensive engineering white papers. These detail an actual upgrade path for building practical, efficient systems today, complete with bills of materials, performance targets, the works.
We are contrasting the historical thunderstick with the modern power solution. This is about moving past the folklore and getting right down to the schematics, the real engineering.
Absolutely. Getting to the schematic.
Okay, let's unpack this then. The historical thunderstick versus the modern power solution. To really understand where we are now and where wireless power might be going, we absolutely have to start with the context of that original vision. Tesla's huge, foundational, world-altering ambition that took him out to Colorado Springs back in 1899. What was really driving him? What was the force behind that massive commitment of time, resources?
Well, Tesla was operating on a scale that, honestly, few engineers before or since have really dared to attempt. It was audacious. He got to Colorado Springs in 1899, stayed through early 1900, and he had a singular, very clearly stated set of objectives for his research facility there. He was focused on three core areas. First, designing and testing transmitters of, well, unheard of power levels, just massive power.
Okay.
Second, researching means of isolating and, interestingly, individualizing the energy transmission. Could you send power only to a specific receiver? That was the key question for him.
Targeted delivery.
Exactly. And third, and this is really crucial, he wanted to determine the laws of propagation of electrical current through the Earth and the atmosphere.
Right, that third point is the really big differentiator from, say, standard radio, isn't it? He wasn't just thinking about Hertzian waves propagating through space.
Not at all.
He was treating the entire planet like a giant capacitor and conductor.
Precisely. His ultimate dream, the sort of holy grail of his life's work, was laid out pretty clearly. The transmission of power from generating station to generating station without any connecting wires. That was the first step.
Okay.
And then a further evolution. Distribute power globally to all points using a modified system. He proposed using the Earth itself and its atmospheric boundary layers as the primary conducting medium. He wanted the planet to be part of the circuit.
Wow. Okay, the planet is a circuit element. That's ambitious.
Just say the least.
And to even try this, he needed a machine of just unbelievable scale, the magnifying transmitter, right? This wasn't just some high-voltage party trick. It was designed to interface with planetary physics. What was the actual scale of that experimental station?
The facility he built out there on Nob Hill in Colorado Springs, it was just astonishing for the time. It housed what was then, and probably still is in some ways, the largest Tesla coil ever constructed. A massive primary coil measuring 49.25 feet that's just over 15 meters in diameter.
15 meters. Diameter.
Yeah. And this was the prototype, you understand, the full-scale test bed for the larger magnifying transmitter he later tried to build at Wharncliffe on Long Island.
The sources describe the output as genuinely cataclysmic. This wasn't just a little buzzing discharge. This was like elemental power being unleashed.
Oh, it was visually terrifying, apparently.
Mm.
And the electrical output was just staggering. We're talking millions of volts. Tesla produced artificial lightning discharges that reached up to 135 feet. That's 41 meters in length.
Wow.
Apparently, it illuminated the countryside for miles around. He was generating these extremely high-frequency, high-voltage standing waves.
And the really incredible part, maybe the anecdotal impact, shows just how far those fields were reaching. The reports from people living nearby, they sound less like science experiments and more like, I don't know, ghost stories or something.
It speaks volumes, doesn't it? About the raw, undamped energy he was just pumping into the local environment. I mean, consider the documented effects. Light bulbs within 100 feet, 30 meters of the lab. Bulbs that were deliberately turned off, disconnected.
Right.
It started to glow dimly, just powered by the stray inductive fields in the air.
Incredible.
Sparks were seen jumping between people's feet in the ground as they walked near the lab. He even talks about horses, supposedly 6 miles away, receiving shocks through their metal shoes, causing them to bolt from their stalls. The field saturation must have been total.
So the atmosphere, the soil, the buildings nearby, everything was just buzzing at his chosen resonant frequency.
Pretty much, yeah.
But maybe the clearest demonstration of its sheer unintended power came from that incident with the local power company.
Yes, the famous fault incident. That's a key piece of evidence. Tesla was running his experiment, drawing several hundred kilowatts of power, when he inadvertently overloaded and faulted a generator set. Not at his lab, but at the Colorado Springs power station, located a full 6 miles, that's 10 kilometers away.
6 miles. That is a huge distance for an unintentional electrical connection, especially back then. I mean, power grids were much less robust, less interconnected than today. How exactly did his high-frequency experiment manage to burn out their low-frequency equipment 6 miles down the road?
Yeah, that's the fascinating part. The key is the frequency difference. The power station dynamos, they were designed to handle low-frequency AC, right? Probably 60 cycles per second, 60 hertz. Their insulation was perfectly adequate for that.
Standard stuff.
Standard stuff. But Tesla was operating his coil in the tens, maybe hundreds of kilohertz range. Much, much higher frequency. His powerful high-frequency currents induced secondary currents into the low-frequency windings of those distant dynamos.
Inductive coupling.
Exactly. And because high-frequency currents couple much more easily across small insulating gaps, they see capacitance where DC sees an open circuit. They basically bypass the physical insulation designed for 60 hertz. They jump through the windings, cause rapid thermal buildup, and destroyed the electrical insulation. Effectively, they burned out the dynamos.
Wow.
It was this massive, completely unintended demonstration of distant, high-power inductive coupling.
It certainly proved he could affect infrastructure miles away, even if the result was, well, destructive in that case.
Indeed.
Okay, let's turn to the method he actually codified, the plan. His 1900 patent, US 645-576, the system of transmission of electrical energy. What was the actual mechanical and electrical setup he proposed in that patent for achieving this global reach?
All right, the patent is the blueprint, really. It describes a generating station with a high-tension transformer standard AC step-up feeding into a high-tension coil. That's the C in his diagram, the magnifying transmitter structure. Now, critically, this coil's secondary circuit had one terminal connected directly to ground, a very good ground connection.
Okay.
And the other terminal connected to an elevated terminal, which he labels D.
Right, the elevated terminal D. Why? Why have that big structure up in the air? Why not just ground both ends or leave the top floating?
The elevated terminal, which he preferred to be like a big spherical or cylindrical conductive envelope, was essential for a couple of reasons. First, it provided necessary terminal capacitance. A large conductive surface high up in the air, it does two things. It lowers the natural resonant frequency of the whole coil system.
Okay.
And, maybe more importantly, it significantly reduces power loss from something called corona discharge.
Corona discharge. That's the visible glow, the hissing sound you get from high voltage points.
Wow. Exactly. It's basically charge leaking inefficiently into the air. By using a large, smooth conductive surface for his top terminal, Tesla could push much, much higher voltages into the system before that massive leakage started happening.
Okay, so he minimizes losses at the transmitter end. He pushes millions of volts into the ground and into this large elevated terminal. What happens next, according to the patent?
So the transmission principle he outlines is this. He generates extremely powerful high-frequency impulses. These produce an electromotive force, a voltage high enough to actually render the upper strata of the atmosphere conductive.
He wanted to ionize the air way up high.
Essentially, yes. Or at least make it significantly more conductive than it normally is.
Yeah.
His aim was then to drive current through the Earth's bulk conductivity.
Using the planet as the wire.
And using that now conductive upper atmosphere as a return path, thereby creating this giant resonant circuit spanning the globe. The receiving station, maybe kilometers or even continents away, would have an identical elevated terminal, D', and a grounded coil system. And critically, it would be perfectly tuned to the exact transmitting frequency, allowing it to efficiently collect that energy flowing through the Earth atmosphere system.
He explicitly stated in his notes, didn't he, that he could achieve 20, 50, maybe even 100 million volts.
Yes. Voltage is high enough, he believed, to overcome that initial atmospheric resistance and really push the current into the planet's natural conductivity path.
And that's the core realization, isn't it? Tesla wasn't trying to generate a standard radio wave like Marconi that just spreads out and dissipates according to the inverse square law.
Precisely. He was trying to establish a global standing wave of electrical current, using the planet itself as the resonant cavity. He wasn't relying primarily on radiation. He was relying on conduction through the Earth and achieving extremely low loss through high Q resonance of the entire system.
That is the philosophical ancestor of the Wharncliffe Tower. One giant tower, one pulse, designed to energize the whole Earth.
That was the dream, a planetary scale sermon in physics.
It truly was. But that brings us right to the pivot point in our discussion today. Tesla's idea, as you said, was sort of to bully the planet into being a wire. Modern engineering, though, looks at this problem and asks, maybe more pragmatically, okay, if we can't afford the regulatory nightmare, the physical cost, the sheer financial burden of a truly planetary system, where can we apply the science of resonance efficiently and, crucially, locally?
That is the essential transition, yeah. The sheer energy, the scale required for a single global resonant system, it's currently seen as prohibitive, maybe even impossible, given regulatory hurdles, atmospheric noise, things like that, which we can touch on later. So the modern approach, encapsulated in these 6 Wharncliffe II architectures we've pulled from our sources, it's a strategic shift. We stop trying to, dominate the entire planet electrically, and we start focusing on disciplined, localized, efficient solutions that reliably move watts over practical, defined distances.
Building networks, not monuments.
Exactly. Building manageable networks, not monolithic monuments.
Okay, and this is where the conversation gets really critical for the learner listening in, right? These 6 architectures move us away from historical speculation and into concrete, testable systems that people are actually working on or could build. Let's walk through the first 3. These seem to deal heavily with optimizing near-field coupling and maybe leveraging local ground physics more cleverly.
Okay, sounds good. Architecture 1 is probably the most direct evolution of Tesla's resonance trick, but adapted for real-world constraints. We call it the resonant power corridor with repeaters.
You mentioned before this is kind of like Wi-Fi for electricity. What does that actually mean in terms of the hardware involved?
It means chaining together extremely high-quality resonant coils. These coils act as midfield relays. The concept recognizes that while a single coil can only transfer power efficiently over a fairly short range, maybe 5-10 meters officially, you can stack that range by placing carefully tuned coils in sequence, like stepping stones.
Okay, but you said extremely high-quality coils. What makes them high quality in this context?
To do this effectively, you need coils with a very high quality factor, or Q.
Q factor.
Yeah.
Let's pause on that for a second. For the learner who might not be deep into RF, what is Q, and why is getting a Q of 300 or more Q greater than or equal to 300 such a challenging target?
Okay, good question. The quality factor, Q, basically measures how efficiently a resonant circuit, like our coil, stores energy versus how quickly it dissipates that energy, mostly as heat due to resistance. So a high Q means very low resistive loss. The energy bounces back and forth many times before decaying. If you have a low Q coil, it acts more like a toaster element, just gets hot and transfers very little power wirelessly.
Right.
Achieving Q over 300 is difficult because it demands extremely low resistance wiring and very precise geometry. This is why engineers specify special materials like Lix wire.
Lix wire. What is that exactly? Why not just use regular thick copper wire?
Good question. Regular solid copper wire is fine at low frequencies like 60 hertz on the wall. But we're operating here in the radio frequencies, typically in regulated ISM bands, industrial, scientific, medical bands, like 6.78 megahertz or 13.56 megahertz. These are chosen for regulatory calm, basically.
Okay.
At these high frequencies, electrical current tends to flow only along the very outer surface of a conductor. It's a phenomenon called the skin effect.
Right, I remember that.
So Litz wire is actually a bundle of many, many fine strands of wire, each individually insulated from the others. This construction effectively increases the available surface area for the current to flow on, minimizing the losses due to skin effect and also proximity effect between windings. It forces the current to use the whole bundle, maximizing that Q factor. Wide copper strap can also work well if shaped correctly.
Okay, so Litz wire or copper strap for high Q, chain these highly efficient coils together. What kind of performance can you realistically expect from this stacking approach?
Well, you might target better than 50% efficiency from the transmitter coil, TX, to the first receiver coil, RX, over maybe a 5-meter span. That sounds pretty good.
Yeah, 50% isn't bad.
But efficiency stacks multiplicatively. If you have 10 hops in your corridor, the cumulative efficiency is 0.5 raised to the power of 10.
Uh-oh, that drops fast.
It drops very fast.
Yeah.
So the end-to-end efficiency over, say, 100 to 150 meters might realistically drop down to maybe 5% to 10%.
Okay, 5 to 10% sounds pretty low. Is that actually useful?
It depends. 5% delivery of, say, a 10-kilowatt source is still 500 watts of usable power at the far end. And 500 watts is extremely useful for applications like powering sensors or controls on large, rotating machinery where slip rings are problematic, or for setting up temporary power corridors on construction sites, or in disaster relief scenarios where laying physical cable is impossible or too slow.
Okay, I see. So it's niche, but valuable. But wait, keeping a chain of 10 coils perfectly glued to the exact same frequency, maybe down to the kilohertz, while environmental factors, temperature, humidity, maybe a truck driving nearby are constantly changing. That sounds like a serious control problem, a technical nightmare almost.
It absolutely requires intelligent control. You can't just set them up and hope for the best. The solution described uses phase-coherent control. This demands relatively sophisticated electronics, often involving devices like a software-defined radio, SDR, and a phase-locked loop PLL system.
SDR and PLL, how do they work together here?
Basically, the SDR acts like a very sensitive receiver that monitors the phase of the RF signal traveling along the entire corridor. It checks if each repeater coil is receiving the signal in the correct phase relationship relative to the one before it.
Okay.
The PLL then acts as the tuner. If the SDR detects a phase drift in one of the repeater coils, maybe it got slightly detuned by temperature, the PLL actively adjusts the driving frequency or phase of that specific repeater coil to bring it back into perfect lockstep with the signal coming from upstream.
Ah, so it's constantly micro-adjusting each link in the chain.
Constantly. Because if a repeater loses that phase coherence, it stops being a helpful relay and instantly becomes a power sink. It starts absorbing energy instead of passing it on. This active control structure is what makes the resonant corridor potentially practical, but yes, also complex to implement reliably.
That's a really disciplined, modern use of resonance. Okay, now let's tackle that ground issue. Tesla wanted to use the planetary ground path. Architecture 2, the ground-assisted microgrid, sounds like it's doing something similar, but maybe creating a highly controlled, localized short circuit. Is that fair?
That's actually a pretty good, if slightly alarming way to put it. Yes. The concept here is intentional local ground conduction, operating at relatively low frequencies. We completely stop relying on or even thinking about planetary resonance. Instead, we engineer a very high-quality, low-resistance local return path through the ground, but strictly bounded to a small defined operational site like a large farm, a vineyard, maybe a mining operation.
And what defines a high-quality ground connection in this specific context? You need something better than just banging a copy rod into the dirt, I assume.
Oh, much better. It's defined by achieving extremely low ground resistance, specifically targeting a total ground path resistance, RG, of less than 0.5 ohms across that entire site. That's very low.
Half an ohm. How do you achieve that?
It requires significant engineered effort. We're talking about deeply driven, copper-clad rods, maybe dozens of them, all tied together electrically with a buried radial mesh of copper wires spreading out from the transmitter point. And sometimes engineers will even use specialized backfill materials around the rods and mesh things like bentonite clay slurries or saline solutions specifically to lower the electrical resistivity of the surrounding soil. The goal is to create a highly conductive volume of earth that you own and control, allowing you to move hundreds of watts safely across your property using this path.
And the source material specifically mentions using low frequencies for this architecture, typically in the 10 to 100 kilohertz range. Why that frequency band? Why not higher or lower?
Yeah, the frequency choice is critical and connects back to physics, specifically the concept of skin depth in a conductor, which in this case is the Earth itself.
Okay, skin depth again. How does it apply to dirt?
Well, at very low utility frequencies, like 60 hertz, the electrical current penetrates quite deep into the Earth, which is good for grounding, but maybe less controlled. At very high frequencies, like the many-hertz range we use for the corridor, the skin effect becomes very pronounced, and the current is constrained mostly to the surface layer, making bulk conduction through the soil inefficient and lossy.
Right.
But in that 10 kilohertz to 100 kilohertz range, the skin depth in typical moist soil is kind of optimal. It's on the order of several meters deep. This allows the current to effectively utilize the bulk of your engineered conductive backfill and that buried radial mesh system, ensuring a reliable, low-resistance conduction path over tens or even hundreds of meters within your fenced or defined property area.
Interesting. So if you use 1 megahertz, you'd lose efficiency because the current stays too close to the surface and maybe radiates more. And if you use 60 hertz, the inductive losses and the size the transformers needed will become prohibitively large and expensive for this kind of power level.
Exactly right. So 10 to 100 kilohertz hits that practical sweet spot for efficient, localized ground conduction.
And the idea is you'd swing maybe plus or minus 200 volts between your transmitter's ground connection and the receiver's ground connection using this engineered path.
Precisely. By driving a voltage, say 200 V, into that very low resistance ground path you've created, you can distribute power quite efficiently across your site. It's like creating your own little localized, single-wire earth return utility grid. A massive conceptual difference from Tesla's global ambition.
Okay, but wait a minute. If you're intentionally pushing hundreds of watts of electrical power into the ground at, say, 20 kilohertz, how do you prevent that from coupling into or interfering with existing underground infrastructure? I'm thinking about things like, municipal water pipes, maybe buried telecommunications cables nearby, even neighboring properties' grounding systems. That seems like a potentially huge regulatory and safety risk.
That is, without a doubt, the primary non-technical challenge for this architecture. You've hit the nail on the head. The system must be explicitly designed to be bounded to the local property, usually requiring a physical fence or at least very clearly demarcated boundaries for an industrial or agricultural site. And the operating frequency must be very tightly controlled and filtered to minimize EMI, electromagnetic interference, radiating outside that boundary.
So careful engineering is needed.
Absolutely. Engineers designing this kind of microgrid have to perform detailed modeling of the potential inductive coupling paths to ensure they don't create dangerous touch voltages on fences or equipment outside the intended operational zone. This is why architecture 2 is really only suitable for private, controlled environments. Large farms, remote mines, maybe certain military installations where the site boundaries are clearly defined, access is restricted, and you have control over what's buried nearby. You wouldn't deploy this in a suburban neighborhood.
Okay, that makes perfect sense. The localized control and boundary definition are absolutely key to the safety envelope. All right, moving on to architecture 3. The phased coil array, or field shaping. That sounds quite different again. More digital, maybe? Sounds like a good solution for dynamic indoor spaces, perhaps?
Yes, this is definitely a more high-tech digital control approach. It's essentially beamforming, but for the reactive near field, not for far-field radio waves. So instead of having just a single transmit coil radiating its magnetic field somewhat omnidirectionally in the near field, use a set an array of maybe 4 to 16 smaller transmit coils. These might be embedded in a floor mat, a charging pad, or maybe along the wall.
Okay, an array of coils.
And here's the clever part.
Yeah.
You drive each coil in that array individually with precisely controllable phase and amplitude for the current flowing through it. By adjusting these phases and amplitudes across the array, you can synthesize or shape the resulting combined reactive magnetic field. The goal is to create a constructive interference pattern, a high-power hotspot at a specific target location, maybe 3 to 15 meters away.
So you're focusing the magnetic energy wirelessly onto a specific spot.
Exactly. You're shaping the near-field energy distribution.
How is shaping a magnetic field like this different from, say, shaping a sound wave using phased array speakers? That's an analogy we sometimes hear.
It's conceptually similar in terms of using phase sources to create constructive and destructive interference. But the physics is different. Sound waves are purely propagating pressure waves. Here, we are primarily manipulating the near-field magnetic energy, the reactive field component, which doesn't radiate away efficiently but stores energy locally. Getting this right requires immense computational power and extremely precise timing synchronization between all the coils in the array. You often need specialized hardware like a field programmable gate array, FPGA, or maybe a direct digital synthesizer, DDS-based clock tree to manage this.
FPGA or DDS. Why is that specialized hardware necessary? Can't you just use a regular computer?
You need incredibly fine control over timing. To achieve the technical goal, which is typically aiming for something like +6 to +12 dB of effective field gain at the focus point compared to what a single coil would produce there.
Okay, that's a significant power increase at the target.
It is. But to get that sharp focus and gain, you need phase resolution between the coils of maybe 1 degree or even less. If your timing is off by just a few degrees at these frequencies, the constructive interference collapses, the focus smears out, your efficiency plummets, and you could potentially create unwanted hotspots elsewhere, which could be dangerous. So the FPGA or DDS provides that microsecond or even nanosecond level of timing precision needed to reliably hit that target focus.
That level of precision and the fact you're creating a high-energy hotspot absolutely screams safety critical, doesn't it? Especially if this array is designed to charge something like an autonomous guided vehicle, AGV, moving around a busy factory floor.
Oh, absolutely safety critical. It's probably the biggest design constraint. Because the energy density right at that focus point can be quite high, the system must incorporate robust foreign object detection, or FOD.
FOD. How does that work in this context?
If any unintended object, say a dropped metal tool, or worse, a person's hand or foot enters that high-energy focus volume, the array has to detect it and react instantly.
How does it detect it?
Usually the presence of a foreign object, especially a conductive or magnetically permeable one, will slightly change the electrical load seen by the coils in the array.
Yeah.
It effectively detunes the resonance in that local area. A sensitive monitoring circuit needs to detect this change in impedance or detuning signature, and the safety interlock must then immediately command the array controller to defocus the field.
Defocus.
By rapidly changing the phase relationships between the coils, basically scrambling the pattern in microseconds to instantly neutralize that high-power hotspot and spread the energy out safely.
Wow. Okay, so it has to fail safe instantly.
Instantly and reliably. This is why the primary use cases are in highly controlled environments. Dedicated AGV charging bays, where the approach path is clear, perhaps powering specific tools in robotic work cells, or precise charging paths for equipment where you can guarantee nothing intrudes unexpectedly.
Got it. So the first three architectures, the corridor, the microgrid, the phased array, they're all fundamentally manipulating resonant near fields or using localized conduction. They're playing clever tricks with Maxwell's equations up close.
That's a good way to put it.
But what if you genuinely need line-of-sight power transfer over much longer distances,
Yeah.
hundreds of meters, maybe even kilometers? That seems like a totally different problem.
It is a totally different problem, and it requires a totally different solution. That brings us to Architecture 4, which represents a decisive break from anything resembling the Tesla model. Architecture 4 is the Rectenna carpet plus microwaves. Our sources sometimes refer to this as the grown-up far-field solution. Here we are moving power using high-frequency electromagnetic radiation, essentially a highly directional radio beam, just like point-to-point microwave communications or radar.
Okay, so we're firmly in the realm of radio waves now. You mentioned high frequencies. Are we talking things like commercial radar bands or satellite communication frequencies like 5.8 gigahertz or even 24 gigahertz?
Correct. Those are typical frequencies considered for power beaming. The transmitter for this architecture would likely utilize a solid-state GaN phased array.
GaN, gallium nitride. Why is that specific semiconductor material important here?
GaN is really essential for this application because it offers significantly higher power density, better efficiency, and can operate effectively at these extremely high microwave frequencies where traditional silicon-based power devices really start to struggle with losses and heat.
Okay, so GaN allows for a powerful, efficient microwave beam.
Exactly. And it's a phased array again, but this time operating in the far field. It focuses the beam very tightly, shaping the EIRP, that's the effective isotropic radiated power, to direct the maximum energy precisely at the receiver location, while crucially staying within strict regulatory RF exposure safety limits everywhere outside that targeted beam path. Beam containment is critical.
Right, and the receiver at the other end, you called it the Rectenna carpet. Tell us about that technology. What is a Rectenna?
Okay, a rectenna, the name is just a portmanteau of rectifying antenna, is actually a pretty sophisticated piece of technology. It's typically built as a tile or panel that combines two functions: a receiving antenna optimized for the specific microwave frequency being used, and a high-speed, high-efficiency rectifier circuit integrated directly with it.
A rectifier, so it converts the incoming AC microwave signal directly into DC.
Exactly. It converts the captured RF energy directly into usable DC electricity right there on the panel. Modern rectenna designs, often using specialized Schottky diodes or even active synchronous rectification at microwave frequencies, can achieve really impressive RF to DC conversion efficiencies. We're often seeing numbers in the range of 75% to 85% reported in research.
Wow, 75–85% RF to DC. That's actually very competitive with the efficiency of, say, a standard power supply converting AC to DC.
It is surprisingly efficient, yes, which makes the whole concept much more viable.
So with enough receiving aperture, meaning a large enough carpet made of these rectenna tiles, what kind of power delivery are we potentially talking about over, say, hundreds of meters line of sight?
Assuming you have clear line of sight, no obstructions, and can deploy a sufficiently large rectenna aperture at the receiving end, the physics suggests you could realistically deliver 10 kilowatts, maybe even significantly more, over distances of hundreds of meters to potentially a few kilometers. This microwave beaming architecture is currently considered the most viable technical option for achieving high-power wireless transfer over genuinely long distances. Think about potential applications like beaming solar power down from an orbital satellite, or maybe moving power across deep canyons or rugged terrain where running physical wires would be astronomically expensive or environmentally disruptive.
Right. It's definitely the least Tesla-like approach in spirit, maybe, but it directly addresses the long-distance power transfer problem in environments where a highly focused beam is feasible and safe.
Precisely. It's pure radio engineering applied to power.
Okay, now let's jump back conceptually towards Tesla's original inspiration with Architecture 5, the Elevated Terminal 2.0. This sounds like it's trying to achieve that crucial high terminal capacitance that Tesla wanted, but without having to build a massive, fixed concrete and steel tower like Wharncliffe.
That's exactly the idea. This architecture is really a pragmatic attempt to address one of Tesla's core geometric requirements for his system. The problem statement is simple. How do you get a large, high-capacitance conductive surface, the top load way up high, maybe 100 to 300 meters into the air, without incurring the enormous cost, rigidity, and vulnerability of building a massive physical tower structure?
Right. If the tower was the problem, what's the modern workaround?
The modern proposed solution is often a tethered aerostat or a specialized kite.
Like a balloon or a blimp.
Sort of. Specifically, designs like a helikite, which combines aspects of a kite and a balloon for stability, or perhaps a small, streamlined blimp could work. The key is that a significant portion of its skin would need to be made conductive, maybe using an aluminized fabric segment. This floating conductive structure then acts as the elevated terminal, fulfilling the same role as Tesla's large copper sphere. It's connected down to your grounded secondary coil on the surface via a specialized tether.
A conductive tether? That sounds tricky.
Yeah, the tether itself is a piece of engineering. It typically needs a high-strength, non-conductive core, maybe Kevlar, to handle the mechanical tension from the wind acting on the aerostat. And then, embedded within or running alongside that core would be the high-voltage conductor needed to carry the potential up from the secondary coil to the elevated terminal.
Okay, so the altitude gives you that desired large physical separation from the ground, increasing capacitance to the environment, and potentially giving cleaner field lines for propagation, just like Tesla intended. But you can launch it and presumably retrieve it when needed.
Exactly. The high terminal capacitance it provides is crucial. It helps dramatically reduce corona discharge losses, especially if you're planning to operate at very high voltages. It also stabilizes the coil's resonance and generally lowers the natural resonant frequency compared to what you could achieve with a short fixed tower of reasonable cost. A lower resonant frequency might, in some theories, improve efficiency for certain types of longer wave ground propagation, although that's still debated.
Okay, I can see the theoretical elegance. It mimics Tesla's geometry without the concrete. But the reality check here must be immense, right? Beyond just the engineering challenges of managing a potentially miles-long conductive tether carrying maybe millions of volts, the regulatory and environmental hurdles must be a complete nightmare.
Oh, the practical challenges are significant, absolutely. Weather is probably the #1 enemy. You obviously can't launch or operate this thing in high winds or anywhere near thunderstorms unless you actively want your setup to become the world's most expensive lightning rod.
Right. Bad idea.
You'd need incredibly sophisticated automated winch systems to manage the tether tension and allow for rapid retrieval in changing conditions.
Oh.
And you'd need massive, absolutely reliable lightning arrestor systems at the ground connection point.
And then there's the sky itself. airspace.
And then there's the whole regulatory compliance side. Launching a tethered object that could potentially reach 300 meters or more into the air requires continuous coordination with aviation authorities, the FAA in the US, for example. You'd almost certainly need to establish clear, restricted, no-fly zones beneath and around your operation, which could be difficult depending on the location. Honestly, the operational complexity, the weather dependency, the safety requirements, and the regulatory burden of launching, maintaining, and retrieving this kind of high-altitude apparatus reliably often seem to outweigh the potential efficiency gains it might offer over other architectures. It's an elegant concept on paper, but very, very challenging to implement practically and safely.
Yeah, it sounds like the paperwork alone could sink the project before you even order the balloon.
Quite possibly.
Okay, all right. Finally, let's look at the sixth architecture described in the sources. Burst mode power plus local storage. This one sounds different again. More like an electrical turbocharge, maybe? An efficiency hack that tries to maximize the coil's performance by hitting it really hard, but only for short periods.
That's precisely what it is. This architecture cleverly exploits a fundamental piece of physics relating to high-Q resonant circuits. The basic idea is that these high-Q coils tend to perform much better, meaning transfer energy more efficiently when they are driven with very high instantaneous currents, provided you don't subject them to the continuous thermal load that running them at that high current continuously would generate.
Okay, so you hit it hard and fast, then let it cool down. Explain the process. How does it actually work step by step?
Okay. At the transmitter station, instead of drawing power directly from the grid and feeding it continuously into the coil driver, you first charge up large banks of energy storage devices. Typically, these would be supercapacitors because they can charge and discharge very rapidly with high current.
Okay, so you trickle charge the supercaps from the grid?
Right. You draw power slowly and continuously from the grid, storing it up in these supercapacitor banks over maybe several seconds or even minutes. Then, once the bank is fully charged, you trigger a switch that dumps that stored energy in a very short, extremely high-power burst. We're talking maybe 100 kilowatts or more into the primary coil of your resonant transmitter. This powerful burst might only last for a fraction of a second, meaning it's delivered at a very low duty cycle. For example, you might pulse at 100 kilowatts for 10 milliseconds, then wait 90 milliseconds before the next pulse, giving you a 10% duty cycle overall. The coil only resonates powerfully for that brief instant, but it sings incredibly loudly, electrically speaking.
Okay, so huge peak power, low average power. What about the receiver side? It needs to handle this sudden spike of energy.
Yes. The receivers for this architecture also need to be equipped with their own local energy storage. Again, typically supercapacitors or maybe small batteries, depending on the load profile. They are designed to absorb that incoming high-power pulse very quickly when it arrives. They then use their onboard storage to smooth that intermittent energy out, providing a nice, continuous, steady power output to whatever device or load is connected to the receiver.
Interesting. Why is this approach considered mechanically and thermally superior to just transmitting the average power continuously?
It comes down to component stress and heat. Let's say you need to deliver an average of 10 kilowatts wirelessly. You could try to run your transmitter continuously, pushing 10 kilowatts through it all the time. But doing that means your power semiconductors, the MOSFETs or IGBTs doing the switching and the copper strap of your primary coil, are subjected to a constant, significant thermal load. This forces you to use massive, expensive heat sinks, maybe liquid cooling, and potentially limits the maximum voltage you can safely run at, all to keep the components from overheating and failing.
Right. Heat is always the enemy.
Always. But by delivering that same average power using, say, 100 kilowatt spikes at only a 10% duty cycle, you significantly reduce the average heat dissipation in those critical components. Yet during that brief on-time, you're driving much higher instantaneous currents through the coil. And theory suggests that the efficiency of energy transfer in these resonant systems often improves at higher operating currents, up to a point before saturation or breakdown. So you're potentially getting better instantaneous transfer efficiency and dramatically reducing the thermal management headache. It's basically smart thermal management disguised as a power delivery strategy.
It's engineering that acknowledges the real-world limitations of material science and thermal dynamics. It sounds clever, but it also seems like it would require incredibly tight synchronization between the transmitter deciding to fire its burst and the receiver being ready to catch it.
Synchronization is absolutely paramount. You're right. If the transmitter fires its 100 kilowatt pulse and the receiver isn't actively tuned and ready to absorb it at that exact instant, that energy either gets wasted, radiating elsewhere, Or worse, it could reflect back from the receiver coil into the transmitter, potentially creating huge voltage spikes that could destroy the transmitter's switching components.
Ouch. Yeah, that sounds bad.
Very bad. So, much like the power corridor architecture, this burst mode approach demands intelligent control systems. There needs to be some kind of communication handshake protocol, however brief, to ensure the receiver acknowledges its readiness before the transmitter controller gives the command to discharge that massive capacitor bank into the coil. Timing is everything.
Okay, wow. We've really moved from Tesla's singular, almost mythical vision of global power to 6 very distinct, modern, and often highly complex engineering approaches, each tailored to specific scenarios and constraints. Now, here's where, for me at least, it gets really interesting, and potentially for you listening too. How do we translate some of this theory into something tangible, something you could potentially experiment with in your own garage or workshop? Our sources provide a pretty concrete Stage A prototype path. They call it the bench proof. What's the goal of this stage, and why is it such an important first step for anyone wanting to learn hands-on?
Yeah, the stage at bench proof is absolutely the foundational experiment you should start with. The goal is really straightforward. Can you demonstrably prove the principle of resonant wireless power coupling over a short but meaningful distance? Specifically, the target is usually zero point 0.5 to 1.0 meter. And can you deliver a functional amount of power? The target here is typically around 100 watts across that gap. This experiment confirms you understand the basic physics and tuning involved before you even think about attempting the much greater complexities of things like phase-coherent corridors or engineered ground paths.
Right. Walk before you run.
Exactly. And the good news is, this Stage S setup is potentially achievable, maybe over a weekend or two, for potentially under $500, if you're resourceful about acquiring some of the parts, which we'll talk about later.
Okay, let's walk through the bill of materials sketch for building this miniature tower, the Stage A setup. What specific components do we need to construct the coils themselves, the heart of the resonator?
Okay, for the resonant parts, you need 3 primary physical components. First, and most critical, is the secondary coil. This is your high-voltage, high-Q component. The sources suggest winding approximately 1,000 turns of quite fine magnet wire, maybe 34 AWG, onto a standard PVC pipe form, perhaps around 60 millimeters, a bit over 2 inches, in diameter. The exact number of turns, the wire gauge, the diameter, and the length of the winding, combined with the top load capacitance, will determine the coil's natural resonant frequency, F0. Precision here matters for Q.
Okay, the 1,000 turns of fine wire, that sounds tedious.
It requires patience, yes. The coil winder helps immensely.
And what about Tesla's essential elevated terminal, the top load? We're obviously not building a giant copper sphere for the garage bench, are we?
No, definitely not. For this scale, we build a toroid-shaped top load. A toroid, like a donut shape, provides a large surface area with smooth curves, which maximizes the capacitance to the environment while minimizing sharp edges where corona discharge could occur, even at the relatively lower voltages we're using here.
How do you make one easily?
Our sources recommend constructing a toroid with an outside diameter, OD, of maybe around 160 millimeters, about 6 inches. And resourceful builders often make these quite effectively using repurposed, flexible aluminum dryer duct, the kind you connect to your clothes dryer. You form it into a circle, tape the ends together, and then maybe wrap the whole thing smoothly in aluminum foil tape to get a good conductive surface.
Ah, dryer duct tech. I like it. So that toroid provides the capacitance needed to lower the resonant frequency and stabilize things?
Exactly. It's essential for getting good resonance and minimizing losses.
Okay, so we have the secondary coil and its toroid top load. Now, what about the primary coil, the component that actually energizes the system from our driver circuit? What are the specs for that?
Right, the primary coil needs to handle more current, so it's physically more robust. Typically, it might be something like 5 turns of much thicker conductor, maybe 12 millimeter wide copper strap, or even copper tubing. And critically, this primary coil needs to be constructed with some kind of adjustable height mechanism relative to the secondary coil.
Adjustable height. Why is that important?
Because the key to achieving maximum power transfer efficiency between the primary driven coil and the secondary resonant coil is tuning the coupling factor, usually denoted as K. This K value depends strongly on the physical proximity and alignment between the two coils.
Ah, okay.
So you need to be able to physically slide the primary coil up or down along the base of the secondary coil to find that sweet spot, the optimal coupling position where you transfer the maximum amount of energy without causing problems like destructive self-resonance or frequency splitting, which can happen if the coupling is too tight. Tuning K is just as important as tuning the frequency.
Got it. Coarse tuning is physical position, fine tuning is frequency. Now, for the really critical part, the electronics. What's actually powering this high-frequency resonance system and why the specific circuit topology mentioned?
For this stage A prototype, the recommended driver is a Class E MOSFET driver. It's typically operated in current modes control for stability and running at a frequency somewhere in the 300 to 400 kilohertz range, matched to the resonance of your secondary coil and toroid.
Classy. Why that specific topology? Why not something simpler?
Class E is vital here because it is a highly efficient resonant switching topology. What that means is it's designed so that the switching element, usually a power MOSFET, turns on and off, ideally when the voltage across it is zero or the current through it is zero.
Zero voltage switching, ZVS, or zero current switching, ZCS?
Exactly, ZBS, ZCS. This minimizes the time the MOSFET spends in that nasty transitional switching state, where it's simultaneously experiencing both high voltage and high current, which is where most of the wasteful switching losses and heat generation occur in simpler topologies.
So it wastes less power as heat, meaning more power goes into the coil.
Precisely. It allows for much higher efficiency, which is critical when you're trying to push power wirelessly. And importantly, for a home build, the driver is typically powered by a relatively safe, low-voltage DC input, maybe 24 to 48 volts.
Okay, safe input voltage, efficient high-frequency output. Now, on the receiver side, sitting maybe 0.5 to 1 meter away, how do we efficiently capture that transmitted energy and convert it back into something useful, like DC power?
The receiver can actually be elegantly simple for this stage.
No.
It typically consists of a basic pickup coil, maybe just 15 turns of wire, wound on a form, and potentially tuned with a capacitor then feeds the captured high-frequency AC energy into a rectifier circuit to convert it back to DC. And for best efficiency, the sources recommend using a synchronous rectifier, SR MOSFET bridge, rather than standard diodes.
Synchronous rectifier. Why use SR MOSFETs instead of just a standard silicon diode bridge, which would certainly be cheaper and simpler to implement?
Efficiency again. Standard silicon diodes have a relatively fixed forward voltage drop, maybe around 0.7 volts per diode. When you're rectifying a relatively low voltage high-frequency signal, that 0.7 or maybe 1.4 volt drop across the bridge represents a significant percentage of the power being wasted as heat in the diodes themselves.
Right, the diode drop really hurts at low voltages.
It does. An SR setup replaces the diodes with MOSFETs. A control circuit actively drives the gates of these MOSFETs, switching them on and off, perfectly in sync with the incoming AC waveform from the pickup coil. When a MOSFET is switched fully on, the resistance across it, its ARDS on, can be extremely low, maybe just a few milliamps, for a good power MOSFET. This results in a much, much lower voltage drop compared to a standard diode.
So way less power wasted in the rectification step.
Dramatically less. This significantly improves the overall RF to DC conversion efficiency of a receiver, which is particularly crucial when you're already fighting the coupling losses inherent in transferring power over that 1 meter distance. Every bit of efficiency counts.
Okay, that makes sense. Use SR for the win. Now let's assume our diligent learner has carefully constructed this intricate system. The coils are wound, the toroid is taped, the classy driver is built, the SR receiver is ready. What's the homework assignment? What are the specific, measurable performance targets that prove the system is genuinely working as intended and properly tuned?
Right. You absolutely need a strict hit list, a set of objective measurements to qualify your build. It's not enough for a light bulb to just glow dimly. First, and arguably most importantly, before you even apply significant power, you must measure the unloaded quality factor Q of your secondary coil with its top load attached.
Measure Q. How do you do that?
You need a specialized instrument called a vector network analyzer, VNA. Luckily, there are now some very affordable USB VNAs available for hobbyists, like the Nano VNA V2, which are perfect for measuring impedance and Q in these frequency ranges, hobby bands. You connect the VNA to the secondary coil, perhaps via a very loose coupling loop, and measure its resonance curve. From that, you calculate the Q. Your absolute target here, according to the sources, is to achieve Q greater than or equal to 250.
Q equals 250. What if you measure, say, only Q equals 50?
If you measure Q50, your coil is frankly pretty useless for efficient resonant power transfer. It means your winding technique was poor, your wire resistance is too high, or maybe your toroid connection is bad. You need to go back and rebuild the secondary until you hit that Q target. Measuring Q first confirms the heart of your resonator is good before you waste time troubleshooting the electronics.
Okay, so measure Q first, aim for 250 plus Harbel. What about the actual power delivery target once you hook everything up?
The key performance target for this stage of bench proof is to successfully deliver 100 watts of power into a suitable dummy load, like a big power resistor, connected to the output of your SR receiver. And you need to achieve this power delivery across that zero point 0.5 to 1.0 meter distance with an overall end-to-end system efficiency, DC input power at the transmitter driver to DC output power at the receiver load, of greater than or equal to 25%. This measurement needs to be taken when the primary coil is positioned at that physical sweet spot for optimal coupling.
100 watts out at 25% efficiency over about a meter. That's a pretty solid benchmark. That's the mark of a successful bench proof, showing you've really got the resonance and coupling dialed in.
It absolutely is. If you can hit those numbers, you've successfully replicated the core physics.
And finally, there's one more crucial check, isn't there? The ultimate physics litmus test, the thermal check.
Yes, absolutely critical for safety and for proving efficiency. You must run a safety and thermal check. While delivering that 100W, you need to carefully monitor the temperature of the primary coil's copper strap or tubing. The requirement is that its temperature rise should be less than 40 degrees Celsius above the ambient room temperature after about 5 minutes of continuous operation at full power.
Less than 40 C rise on the primary. Why is that specific check so important?
Because if that primary coil is getting excessively hot, it's a direct indication that something is wrong. It means too much energy is being wasted as heat, I2 at Railow's losses, in the primary itself. This could be because your coupling factor, K, is poor, too much current circulating only in the primary. Your primary coil's own Q is too low, too much resistance, or perhaps your Class E driver isn't properly tuned, not achieving true ZVS-CCS, leading to excessive switching losses, which then heat the primary through reflected impedance.
So wasted power directly manifests as heat.
Exactly. And excessive heat will not only lower your efficiency further, but it will quickly lead to catastrophic failure, melting insulation, desoldering connections, or even destroying your expensive MOSFETs in the driver. That thermal check is your proof that you've truly mastered the resonant energy transfer, not just cobbled together parts that get hot.
Right. That thermal margin is fundamentally the difference between a successful, sustainable experiment and a brief flash followed by smoke and disappointment.
Absolutely. The laws of thermodynamics are always the final regulators of any electrical system, especially high-power ones. You can't cheat them.
Okay, this Stage A build sounds achievable. But getting all the specific parts, the right MOSFETs, the high Q capacitors, maybe even the VNA could still add up. This brings us perfectly to the philosophy of the scrappy engineer. Practical builds, especially ambitious ones like these, can get incredibly expensive if you buy everything brand new from major suppliers. Our sources provide an excellent inventory, almost a treasure map, for salvage targets. They show how you might build a system that looks like it needs $5,000 worth of new parts for maybe under $500 just by resourcefully sourcing components from discarded commercial and industrial gear.
This is absolutely critical knowledge for the learner, for anyone wanting to experiment without breaking the bank. You often don't need to buy exotic parts new. You need to learn how to recognize and map the components found inside existing industrial equipment failures to your specific project needs. This is how you build Wharncliffe 2, or at least Stage A, on a realistic budget.
All right, let's name some names. What are the prime salvage targets? For building that high-frequency Class E coil driver we just discussed, the sources point strongly towards dead induction cooktops and maybe portable induction heaters. Why are these specific appliances such component gold mines?
Because an induction cooktop is essentially just a high-frequency, resonant switching power supply that's specifically designed for relatively high power and considerable electrical robustness it has to survive, pots boiling over, etc.
Yeah.
When you open one up, especially a non-working one you got for free or very cheap, you can often harvest the core power components. The full bridge or half bridge IGBTs, insulated gate bipolar transistors, or maybe high-power MOSFETs used for the switching. You also find the specialized gate driver ICs needed to switch these power devices quickly and cleanly at high frequencies.
Okay, power switches and drivers.
Right.
What else?
Most critically, you often find the large, high-quality polypropylene resonant capacitors. These film capacitors are specifically designed to handle the high RMS currents encountered in resonant circuits operating at tens or hundreds of kilohertz. They are incredibly expensive to buy new in these voltage and capacitance ratings, but they're often perfectly fine in a dead cooktop where maybe the control board failed. You also usually get excellent aluminum heat sinks already sized for the power devices.
Right. And the immediate use case is obvious. This harvested hardware forms the core foundation for building that, say, 500-watt Class E coil driver needed for the Stage A prototype, running perhaps in the 80 to 200 kilohertz range, lower than the MicroGrids corridor, but suitable for this scale.
It's exactly right. The scrappy recipe described is beautifully simple. Carefully extract the main power board. Keep the original power bridge, the IGBT's MOSFETs, and the associated gate driver circuitry. You'll likely need to bypass or replace the original microcontroller MCU brain with your own custom oscillator circuit. This could be as simple as a 555 timer configured correctly, or maybe a small microcontroller board like an Arduino generating the drive signal, or even a cheap DDS signal generator module for more precise frequency control.
And you reuse the big resonant capacitor bank that was already on the board, likely mounted on the original heatsink.
Precisely. Reuse the caps, reuse the heatsink. With a bit of careful modification, you've essentially converted a dead piece of kitchen equipment into a functional, relatively high-power RF transmitter base. Yes, brilliant salvage.
Okay, fantastic for the classy driver. Now, what about architecture too? The ground-assisted microgrid. That needed a different kind of driver, something capable of push-pull H-bridge operation at lower frequencies, maybe 5 to 30 kilohertz, but potentially handling much higher currents to drive that ground path. Where do you scavenge parts for that?
Right. Different requirements demand different donor hardware. For those specific needs, lower frequency, high current, H-bridge topology, your prime salvage targets shift towards industrial automation failures. Specifically, look for broken variable frequency drive, VFDs, or large servo drives that are commonly used to control AC induction motors or servo motors in factories.
VFDs and servo drives.
Yeah.
Okay. What makes them suitable?
VFDs are designed to take incoming AC power, rectify it to a high-voltage DC bus, and then chop that DC using an H-bridge or a similar topology to create a variable frequency, variable voltage output to drive a motor. While they usually operate below 60 Hz output, their internal components are built to handle very high power and current levels. Inside a dead VFD, especially a larger one, you can often find enormous IGBT bricks, single modules containing multiple high-power IGBTs capable of handling hundreds of amps. You'll also find massive DC link capacitors. These are the large electrolytic capacitors that smooth the rectified DC bus voltage, which are great for energy storage. And again, you'll find robust gate drivers designed for these high-power devices.
That makes perfect sense. VFDs are literally designed to shove series power into heavy inductive loads like three-phase motors. So you need exactly those kinds of rugged, high-current components to effectively swing hundreds of volts into your engineered local ground path for the microgrid architecture.
Precisely. The components are ideally matched to that task profile.
Okay, now for managing all the heat these systems generate, especially maybe Architecture 6 burst mode, where you have high peak powers, and also for bulk energy storage needs. The sources mentioned looking at broken pro audio power amplifiers. That seems like an odd source.
It might seem odd initially, but high-end professional audio power amplifiers, the kind used for large concerts or installations, are another hidden gem for the power electronic salvager. Think about brands like Crown, QSC, Lab Group, and when these high-power amps fail, often due to abuse or maybe just age, they frequently get sold off very cheaply as blown or for parts only. While the sensitive audio signal path might be damaged, the core power supply and thermal management infrastructure is often salvageable and incredibly robust.
What kind of useful parts do you get?
You get massive, beautifully engineered, finned aluminum heat sinks. These are absolutely essential for managing the thermal load in high-power drivers, maybe especially for the continuous operation parts of the burst mode system, or just keeping a high-power Class E driver cool. You also often find large toroidal power transformers, which are great for isolating your project from the mains or for creating different voltage rails. And critically, these amps contain enormous bulk electrolytic capacitors for their power supply, filtering, perfect for building up the high current DC bus stages needed in many of these architectures, or even as part of the storage bank for burst mode.
So you essentially strip out the delicate audio circuitry, but salvage the heavy-duty mechanical structure and the power conditioning backbone.
Exactly. You leverage the fact that audio companies already solved the problem of packaging high power and managing heat effectively.
Resourcefulness really is the foundation of practical engineering, isn't it?
It truly is. And speaking of practicalities, we also absolutely need diagnostic tools. That affordable Nano VNA V2 we mentioned is almost indispensable for measuring Q and finding the exact resonant frequency of your coils. You can't tune effectively without it. And please, always do your nickel testing and bring up using a current limited laboratory power supply. Never, ever just plug a newly built high-power driver directly into the full wall voltage or a high-capacity battery until you've carefully confirmed its basic operation, tuning, and current draw at a much lower, safer power level first. That's how you avoid expensive explosions.
Absolutely crucial advice. Build it, test it low, then ramp it up carefully. Okay, before we move away from the workbench and the salvage pile, we absolutely must dedicate sufficient time to safety. It was mentioned throughout, but let's focus on it. When you're dealing with salvaged industrial components, especially things like large capacitors and high voltage transformers, the danger is often invisible and potentially lethal.
The dangers are significant and absolutely non-negotiable. There are no shortcuts here. Rule number one when dealing with salvage power components relates to thermal management. If you scavenge parts designed to handle hundreds or thousands of watts, they will generate significant heat when you use them. You must mount them properly on adequate heat sinks, often the ones they came with, and ensure good airflow. Overheating leads to failure, and failure can be dangerous.
Okay, manage the heat. What's rule number 2?
Rule 2 is the profound danger of stored electrical energy, particularly in capacitors. Large DC link capacitors, like those found in VFDs or big power supplies, can hold a dangerous, even lethal charge for minutes, hours, days, or sometimes even weeks after the main power has been disconnected.
Days or weeks. Wow.
Yes. You absolutely cannot assume a capacitor is discharged just because the plug is pulled. Therefore, always, without any exception, use proper bleed resistors in your circuit designs to help drain them automatically. Though, don't rely solely on these. And, critically, always use a dedicated, properly rated discharge stick with a built-in resistor to manually short the terminals of all large capacitors every single time you are about to touch or interact with the circuit, even if you just pulled it off the storage shelf 5 minutes ago. Verify 0 volts with a meter afterwards. Assume nothing.
Discharge sticks and bleed resistors. Non-negotiable. Okay. What about the hazards specific to these wireless power systems or the high-frequency fields themselves? RF exposure.
Right. When you start operating these coils, especially as you scale up the power beyond the basic stage A level, you are generating strong, high-frequency electromagnetic fields. High-power Tesla coil demonstrations, or systems like the power corridor or the phased array, must be treated with the same respect you'd give a radar installation or a high-power radio transmitter. The area must be physically fenced off or clearly cordoned off during operation. Power must be killed instantly if anyone or anything intrudes into the safety zone. While the power levels in the DIY Stage A are relatively modest, when you get up into the kilowatt range needed for some of the more ambitious architectures, the intense RF magnetic fields can potentially induce dangerous currents in nearby metallic objects, like jewelry, tools, or medical implants. And prolonged exposure to very high RF fields can potentially cause deep tissue heating in humans, even if you don't feel it immediately.
So distance and shielding are key.
Distance, shielding, interlocks, and awareness. This is a crucial ethical and engineering responsibility when working with these systems. You are dealing with serious, potentially hazardous levels of electrical power and RF energy. Don't become complacent.
Safety first, physics second, always.
Well said.
Full stop.
Okay, let's try to pull all of this incredible analysis together now. We started our journey way back with Nikola Tesla's truly grand, almost unimaginable vision. A single planetary resonant pulse using the Earth and the atmosphere themselves as the transmission medium. One tower to power the world. We then dissected 6 very concrete modern engineering paths, the Wharncliffe 2 architectures, which, while inspired by Tesla's resonance concepts perhaps, are overwhelmingly focused on efficiency, precise control, and maybe most importantly, localization of the power transfer.
Yeah, I think the final analysis really boils down to that core dichotomy, global versus local. Tesla's goal was undeniably revolutionary, aiming for a paradigm shift in global energy distribution. But the sources we've looked at, reflecting modern understanding, show pretty clearly that current physics knowledge, material science limitations, and the sheer regulatory and atmospheric complexities make that single global system seem incredibly difficult, perhaps practically impossible, at least for now. So modern engineering effort has pivoted. It dictates using networks like the corridor, arrays like the phased array, localized phenomena like the ground microgrid, or directed beams like the microwave system to move watts reliably and efficiently today over defined, manageable distances. When you're faced with a practical, immediate engineering necessity like needing temporary power on a construction site or charging complex AGVs in a factory, or getting power onto large rotating equipment without mechanical contacts, these localized resonance techniques, controlled ground conduction, or focused RF beams, are proving to be the clear, efficient, and achievable winners in the near term.
The big lesson here seems to be that wireless power is definitely not some monolithic future fantasy waiting to be unlocked by a single magic bullet. Instead, it's a collection of highly tailored, real-world engineering solutions, each addressing specific power transfer challenges with different physical principles and trade-offs. The sources we discussed laid out 6 different viable paths, and the underlying message seems to be: If a proposed design doesn't actually move significant watts efficiently and reliably from point A to point B, it simply doesn't make the cut in practical engineering terms.
Exactly. That pragmatic focus on moving watts is key. The conceptual shift we've seen, from Tesla's planetary sermons, as you call them, to things like precisely phase-locked resonant corridors or carefully engineered ground paths or safety-interlocked phased arrays. That focus on measurable, controllable, localized performance is the true engineering legacy of this field's evolution.
It really moves the whole discussion from these kind of idealistic, often unmeasurable historical concepts toward repeatable experiments, measurable results, and concrete data sheets.
Precisely. It transforms it from a fascinating philosophy into a working branch of applied physics and electrical engineering.
So, what does this all mean for you, the listener? Hopefully, you now have a much richer understanding the deep historical context of Tesla's original ambition, the detailed blueprints for 6 very different modern approaches being explored, and even a concrete bill of materials and methodology if you're brave enough to try building your own stage and miniature tower. You can now directly engage with the fundamental science, the real challenges, and the potential applications of resonant and radiative wireless power transmission. The fantasy has been grounded, perhaps. The real engineering begins.
And this final synthesis actually leads us back to a really fascinating historical footnote, almost a mystery, from Tesla's time in Colorado Springs. During his incredibly intensive experiments there, pushing millions of volts into the Earth and atmosphere, Tesla meticulously documented observing what he called unusual signals on his highly sensitive receiving equipment. Regular repeating patterns that didn't seem like natural atmospheric noise, like lightning.
Unusual signals. What did he think they were?
Well, based on his interpretation of these faint rhythmic signals, he famously and controversially concluded that they might actually be intelligent communications originating from another planet. He speculated publicly that he might be intercepting early wireless messages from inhabitants of Mars, who he presumed might be more advanced.
Wow, he thought he was hearing Martians. That's quite a leap.
It was a huge leap and widely criticized at the time. However, modern historians, looking back with the benefit of knowing how radio technology was developing elsewhere, now hypothesize something perhaps even more poignant. They suggest Tesla may have inadvertently intercepted the very faint long-distance high-frequency emissions of other early terrestrial radio experiments. Perhaps even the very first transatlantic test signals being attempted by his rival, Guglielmo Marconi, from Europe around that same time period.
No way. So Tesla might have been sitting there in Colorado thinking he was making first contact with Martians, when in reality, he might have just been picking up the faint buzz of a fellow human scientist trying to transmit Morse code across the Atlantic Ocean for the first time.
It's a compelling theory, isn't it? A stunning moment of potential misconnection in scientific history. And it brings us full circle. Given the intense focus required in modern wireless power engineering needing sophisticated SDRs and PLLs just to maintain precise phase coherence over maybe 100 meters in a relatively clean power corridor, consider this final provocative thought. If achieving even local coherence and efficiency is such a complex control problem today, what staggering level of global continuous synchronization, battling unimaginable levels of natural atmospheric noise, terrestrial interference, and unpredictable variations in the Earth's own conductivity? What unseen layers of complexity would Tesla have actually needed to overcome to make his ultimate dream work? To achieve truly global power distribution using a single planet-spanning resonant pulse. Was the eventual failure of the Wharncliffe project less about the funding drying up and perhaps more about the simply insurmountable atmospheric and terrestrial signal complexity, the sheer chaotic noise floor of the planet that was lurking unseen within the physics of that single, ambitious, global resonance circuit he was trying to excite?
A truly high-voltage thought indeed to leave you with, exploring the possibility that the physics of the planet itself, the very medium he sought to use, might have been far more complex and unruly than even the great Nikola Tesla could fully anticipate or manage. Thank you for joining us on this deep dive as we unpacked the high-voltage history, the complex modern realities, and the scrappy hands-on hardware of wireless power transmission.
It's been fascinating. Until next time.